we'll continue with the exploration of exponential functions. And in GeoGebra, I'll just take a new page here. And the first function I want to type in is 2 to the power of x, like this. And I'm going to set up a table that looks like this. So my first function is y equals 2 to the power of x. The next one is e to the power of x. So I'm going to draw that one too. E to the power of x. And this mysterious number e, I mean, when you type this in GeoGebra, you can actually see the value of e. It's not 2.72. It's actually an irrational number. It cannot be written as a fraction. And it does have an infinite number of decimals. So if I set this to 10 decimals, you can keep going, 13, 15. It's not going to end. But I'll leave it at, let's say, 4 decimals, so you can see what it sort of looks like. And this number e to the power of x, oops, like this. That's my second function here. Let's see. There you go. E to the power of x and 2 to the power of x. And the third one I want is, let's see, 3 to the power of x. So I type in 3 to the power of x and enter. So I have 3 functions here. Now, I want to examine the first one I put in. And that was 2 to the power of x. And in my table, you can see that I've put in some x values here. X equals 1, x equals 2, x equals 3, and x equals 4. Now, if I have the x value here and I have my function value here in this column, then 2 to the power of x in this case would be 2 to the power of 1. But I could type in a formula 2 to the power of this cell, and that would give me the value 2. And if I copy this down, oops, no, 2 to the power of 1. If I copy this down, that would give me the function values for x equals 2, x equals 3, x equals 4. So this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. Now, there's a column called rate. And I want to look at the growth rate at these exact points in time, if you like. So when x is 1, what is the growth rate? Or the rate of change? And the way to find the rate of change is, that would be the gradient at this point here. But what is the gradient here? Well, the way we find a gradient to a point on a curve is to take the tangent to that point. So first we need to put in a point here where x is 1 and y equals 2. And you can see I hit the mark here, 1 and 2. If I want to put in a tangent to that point, I go to this menu here, tangents, and I click on a point and I click on the curve. And now I can read off the gradient of that tangent. It's 1.39. If I want more decimals with that, I'll go to settings, I'll set that to 3 decimal places. And that's the tangent. So 1.386 would be the rate of change for this this column here. Now I could do the same with the rest of them and find the rate of change where the x is 2. That would be this point here where x is 2 and y is 4. I would have to find another tangent, and the tangent looks different. It's a bit steeper and it has a different gradient. It's 2.773. If you do that with the first 4 points, you'll get these values here. Now you may notice I've written geometric sequence down here. So what was that thing about geometric sequences? Is that when you took one number in a sequence and you divided it by the previous number in the sequence, you would get what we called a ratio. So if I take this number here, 8, and I divide that by the previous number, 4, I would get the number 2. So this, and if I get the same number for, say, 4 divided by 2, then this is a geometric sequence. Now, if I take, if we look at the rates of change, if I take this number here and divide this by that number, what do I get? Okay, so I get 2.00 something. I take that number here. Oops. This number divided by that number. What does that give me? All right, so there's something going on here. And the first question that you can try to answer is this one here. So how does the value of the base in an exponential function affect the rate of change? Or what is the connection, if any, between base number and rate of change? Now, we do a similar thing with this y equals 3 to the power of x function. Let's see, equals 3 to the power of 1. Like this, and we copy that down. So this is 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, and so on. And we can do the same with the growth rates to that other function of ours. So now we want to see the 3 to the power of x function instead, and we'll find similar points. So we have points 1, 3, 2, 9, and 3, 27, and we want to find tangents to those points as well. And then you can look at the gradients of the tangents and put them in the table. So 3.296, 296, and the next one is 9.888. The next one is 29.663, and so on. And the final one is e to the power of x. I'm just going to clean the slate here and put this in anew. change the view a little bit. All right. So if we want to put in these points, it's a bit difficult to hit the mark. I try to nail the point 1 where it hits the graph. You know, I'm not going to hit it exactly. So I could write the points like this instead. And I suppose I could write the function value like this. Should work. Yeah. So there I have my first point. So 1 and then the number e, because e to the power of 1 is e. My next point is 2 and then e to the power of 2. And my third point is 3 and then 3 to the power of e to the power of 3. And the fourth point is 4 and then e to the power of 4. Like that. And we just change the view a little bit so that we can see all 4 points. And now we want to get the tangent in place as well. First one is down here, second one is here, third one, and the fourth, like that. Now, in our table, we can write off the function values 2.72, 2.72, and 7.39, 7.39, 20.09, 20.09, and the last one is 54.6. And now let's have a look at the tangent. So the tangent for the first one, in this point here, we can look at the gradient of the tangent, and it's 2.72. The next one is 7.39. Ah, look at that. So what you can notice here is that the gradient of the tangent here is actually the same as the function value. And the second question that I want you to answer is, what is special about the number e in this context? So how does the value of the base affect the rate of change? So we've looked at the functions 2 to the power of x, 3 to the power of x, and also e to the power of x. What is special about the number e?